Hello everyone. By now you know that circuit analysis basically is an algorithm that can be followed by anyone, including computers, in order to calculate all the voltages and currents in any network of components connected to each other. One of the pieces of that algorithm, as you may recall, the third part in the three-step process that I introduced to you is actually doing the math, which comes right after writing all the equations that define the operation of all the components in the circuit, plus the KCL. And that set of equations is what captures the operation or the physics of the circuit. And once you mathematically solve that, you get all the unknowns. And in the case of circuit analysis, those unknowns are the voltages and currents in the circuit. Now, it's no secret that there's actually an algorithm for solving set of equations as well, specifically solving a set of linear equations. And in this lecture, I'm opening up a parenthesis, teaching you a little bit about that algorithm, which is pure math. It really doesn't have much to do with circuit analysis or this course for that matter. The material I'm presenting is also presented in Appendix A in the book. You can review it there. It should be a relatively quick review of that appendix. What I'm trying to accomplish here is to show you that even if you don't have one of those fancy calculators, as long as your calculator can actually calculate inverse of matrices, you should still be able to use your calculator and basically get to the final values for the unknowns in your circuit. Now, this system of equations that I have written already here is of the order 3. How we basically assign orders to our equations is basically the number of unknowns in the system. So we have everything is based on voltages in this specific set of equations. So we have V1, V2, and V3 as the unknowns. And this could be a result of writing the equations for a certain circuit. That doesn't matter. That's not of importance at this point. We just look at this purely in mathematic terms when we're trying to calculate or solve this set of equations. So the first thing that I'm going to do in order to explain this algorithm is to move all the unknowns. So let me circle out unknowns. So V1, V2, V2 and V3, V1 and V3. I'm going to move all of the components that have an unknown to one side of the equations. Let's say the left side of the equations. And then all the values that are knowns to the other side. So I'm rewriting that equation so that all the unknowns are on the left. So move V2 to the other side, equal to 4. The second equation becomes 4 times V2 plus V3 is equal to 16. And the third row finally becomes, let me actually play with this a little bit. 2 times V3 plus 7 V1 is equal to 5. Once I have this set, I'm going to explain to you something that most likely is obvious to all of you. So if I have one equation that says a constant A times an unknown X is equal to B, we all agree that the value for the unknown is actually equal to B divided by A. You can rewrite the same solution in this form. You can say B to the power of minus 1 times A, which is the inverse of B, B being a constant in this specific case. And then multiply, sorry, mistake. So this would be A minus times B. So inverse of A multiplied by B, that would be the value for X. Keep that in mind. We're going to go back to it. So I can take this set and write the same set of equation in a different language. How do I do that? Start by putting all the unknowns into an array of v1, v2, v3 arranged in a vector or a 3x1 matrix, and on the other side I'm going to do the same thing. I'm going to put all the known values in the same form of arrangement. And now what's left is this matrix of multipliers that get multiplied by v1, v2, and v3 and give us the equations. So how do we figure that out? So these are the multipliers that I'm looking for. We look at the first equation. We take 2 as the first multiplier for v1, put it here. Look at the second multiplier for v2. So 2 was multiplied by v1. Minus 1 is multiplied by v2, and there is no multiplier for v3 in the first row of this set of equations. So with that, now I have written the first equation in this new format. How do we double check? We take this row, rotate it 90 degrees, multiply all the components element by each other, add them up, and equate to the first number on the other side, and that should give me the same equation that I had. So let's try that. 2 times v1 minus 1 times v2, 0 times v3, which is 0, is equal to 4, which is the same equation. Now I repeat the same thing with the 2 rows that are left. So for v1, I don't have any multiplier. For v2, I have 4, and for v3, I have 1. And finally here, for v1, see, I intentionally moved this so that v1 actually comes second, but once you're writing this equation, you have to be careful. You either make sure that the order is properly done, or if you haven't made that arrangement, then you have to be careful when you're taking the multiplier. You have to take the multiplier for v1 as the first number that you put here, and then second v2 doesn't have a multiplier, and finally 2. So now I have rewritten this set of equations in this new language, or in this new form. Now what I can do is to call this matrix A. This would be the vector of unknowns. I'm going to call it, say, vector V. And finally, on the other side, this is the vector of knowns B. So this equation is basically A times V equal to B. So notice that this is very similar to what we had before. The only difference is that when I was writing this, initially I meant for X to be just a 1x1 matrix, or just one unknown, and A and B were 2 constants. Now you can expand this solution to the case where A is a matrix, your X is a vector, and B is also a vector. In other words, if that's the equation that you have, the vector V is still equal to the inverse of matrix A, in this case, multiplied by vector B. And once you have done this, you get one vector, and a 1-to-1 correspondency is going to give you all the values for v1, v2, and v3. So, in other words, I can say v1, v2, and v3 are equal to the matrix 2, minus 1, 0, 0, 4, 1, 7, 0, 2, inversed, multiplied by the vector 4, 16, and 5. So if I know how to do the inverse of a 3x3 matrix, and then multiply it by this vector, which the inverse of this 3 by 3 matrix is going to be another 3 by 3 matrix, and I know how to do the multiplication. I get every one of the rows rotated 90 degrees, multiply element by element, add them up, that becomes the first element, and then repeat the same thing for the second and the third row, and I get a one-to-one correspondency for each one of the values. In other words, I have the unknown values calculated using this. The only part that is left for us to do is to calculate the inverse of the matrix, the 3 by 3 matrix that we see here. Like I said, if your calculator doesn't calculate the set of equations, there's still a chance that the calculator does calculate the inverse of matrices. So you can actually enter this matrix, calculate the inverse, multiply it by the other vector, and get all the unknown values in that manner. Even if you don't have a calculator that calculates the inverse of a matrix, if you go all the way to this point, in any of the quizzes or exams that you do, all will give you about 90% of the credit for that specific question, or that specific part of the question that you're doing. Doing the inverse of a matrix is not, just keep in mind that it's not as simple as just taking each element and inversing each element one by one. It's more complicated than that. I don't have the time to go through that process and explain to you how to do that. It is explained in the book, at least for a certain kind of matrix. As the order of the matrix increases, this calculation becomes more complicated and harder to do with hand. But nevertheless, the algorithm is valid regardless of the order or the number of unknowns in the set of equations that you're trying to solve. I hope this has helped. Now with this, really we conclude, now at this point we can conclude the circuit analysis is obviously an algorithm that can be followed by computers or any other machine, and if we want to do circuit analysis, we can actually follow the same algorithm and always get the answers. Thank you for your attention. We're going to continue and go back to the main topic from the next lecture, which is circuit analysis.